Hi everyone, hope you're all doing well. So we're going to start section 4.2, right? So this will be on your next test, or test 4, right? And so we're going to sort of continue about talking about integration, right? So on your last test, 4.1, you had indefinite integrals, right? Those are the ones with the plus c. So we're now going to talk about definite integrals, which involve, right, so the reason for that is that they actually calculate the area under various curves, right? Curves represented as functions, right? Like a parabola, right? F of x equals x squared. So, right, so later on we'll be able to determine the area, say, beneath a parabola, right? Before we can talk about that, though, we have to talk about summation notation, right? Summation notation is just a way to represent adding up a whole bunch of things, right? And the symbol for a sum in math is the Greek letter sigma, capital sigma. And so this is just going to mean we're going to add up a bunch of things. This is going to be a sum of something, okay? And yeah. So, for example, right, let's suppose you want to add up the first 15 numbers. Oh, let's just make it the first 10 non-negative integers, right? So we want to add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, right? Well, again, not a hard problem, but one that, you're probably going to plug in your calculator, right? And, yeah, I think it's 55. Yeah, I think the answer is 55. I mean, you might want to double check that, but I'm pretty sure that's correct, right? Okay, so not a hard problem, right? However, suppose instead of going from 1 to 10, we want to go from 1 to 100. Now, you can see the problem. Writing this out, not much less calculating it, but writing out all 100 numbers here could take a while, right? And so, we can't write them all out. It would just take too long. So, ... just that, right? So this ellipses just means that, we're skipping a whole bunch of numbers, right? And where do we want it? We want to end at 100, right? But before we get to 100, let's write out a few more terms. How about 96, right? 97, 98, 99, and finally we end at 100. Okay, right. So even that's a clumsy way to write the sum. And now it's even more difficult. How do you get the sum of all these numbers, right? Well, you can use your calculator, but even that'll take a long time. You're just, punching in a whole bunch of numbers here, right? So, so there's got to be an easier way than just taking 1 plus 2 is 3, right? 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, then 21, then 28. I mean, that's not hard at first, but when you get to 73, it's unpleasant, right? Very tedious, very cumbersome. There's got to be an easier way, and there is, right? That's the whole thing. Before so before we get to the answer here, I just want to show you that, right, this is the power of this symbol here, this summation symbol. We can write this rather than write out all these numbers. We can simply say, look, we want to take a sum, right? The Greek letter sigma for sum. We want to add up what? We want to add up numbers here, right? We can call them n for numbers. It turns out that we're going to use n for something else. So I'm going to use the letter j to represent each one of these, right? So j is a variable, right? It's a variable, but it's not a continuous variable. It's not like, like an x, right? Because x could represent 1, 2, 3, but it could also represent, 4.78. It could represent the square root of 101, right? So x is a real valued variable. J is just an integer, right? Okay, so we're adding up the j's, right? J will go from 1 to 100. So we have to tell it, where are we starting? We're starting at j equals 1. That's the smallest number. And the biggest number is the 100. So we'll put that on the top, right? So this is just a much more convenient, compact way, this here, to write out all of these numbers here. It means the same thing, right? It means that you're starting at j equals 1, and then adding j equals 2, then j equals 3, and so on until you get to the top number here, which is 100. Okay? All right, so again, that's just a convenient way to write it. It doesn't give you the answer. We still don't know the solution. We don't know the actual sum here, right? What's the sum of the first 100 positive integers, right? So it's a trick, right? And if you haven't seen it before, it's pretty clever. You know, there's a possibly apocryphal story about Gauss, who came up with this when he was, 7 years old. It's possible, but it's a story. I'm not sure it's true. Anyways, right? Instead of going 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and so on. What Gauss ostensibly did here is he looked at 1 plus 100. So he added the first number and the last number, right? And 1 plus 100 is, 101, right? So we're going to get 101, right? And then you add 2 plus 99, right? So the second number and the second to last number. Well, 2 plus 99 is also 101. Huh. Isn't that neat, right? Let's keep going. What about 3 and 98? Sure, 3 plus 98 is 101. So there you go, right? You're just adding up these pairs of numbers, and you're always getting 101. So now the question is, well, we add up a bunch of 101s, how many times, right? How many pairs of numbers do we have? Well, if we have 100 numbers, we have half of those, right? 50 pairs, right? So there's going to be 50 pairs of numbers, each adding up to 101. So you just have to do 50 times 101. And that's 5,050. And there you go. That's the answer, right? So we have our answer, finally. Just erasing this, right? The sum of the first 100 positive integers is 5,050. Okay, neat trick, right? All right, now let's do another one. Right? Suppose we want to add. Well, I guess I'll call this example 2. Suppose we want to find the sum. Let's say j goes from 5 to 30. So what is that going to be, right? That's going to be 5 plus 6 plus 7 plus 8, and then we end at 29 plus 30. Okay. And you can see it's a little shorter than the one we just did, right? I mean, if I want to make, well, actually, let's make this harder. Let's go to 300, right? So 299 to 300. Okay. Yeah. Now we're not going to try to do it one by one, right? We're going to use this trick here. Right. Actually, but okay, you know what? Hang on to that thought, right? We're going to get to this. We're going to get to this, but it might be easier before we do this to actually write out what this is as a formula here, right? So as a formula, if we want to go, we want the sum j going from 1 to n, right? So that means 1 plus 2 plus 3 all the way up to, n minus 1, and then ending at n. So here's what you do, right? You take the number of pairs of numbers. Now, right, how many pairs of numbers do we have? Well, like before, you just take n over 2, right? That's how many pairs of numbers. That's the 50 here, right? And what's the biggest number, right? It's n plus 1, right? Because you add the 100 plus the first number is 1. So this is just going to be n plus 1, right? And you can write this as n times n plus 1 over 2. Right, that's a plus. Right. So there you go, right? This is a very convenient formula to get the sum of the first n numbers, the first n integers, right? Now, how does that help here? Because, as you can see, we're not starting at 1, we're starting at 5, right? So that's going to be seemingly a little bit trickier. Okay, but you can think of it as essentially done the same way, right? So even though this was not the question, let's start at j equals 1 and then go all the way to 300, right? So that's going to be 1 plus 2 plus 3 plus 4, right? Plus 5 plus 6 plus 7 and so on up until you get to 300. Right? And now we have a formula for that, right? This is going to be n, which is 300, times n plus 1, which is 301, all divided by 2. Okay, and of course I need a calculator for that. So give me 1 second here. This is going to be 150 times 301. So it's going to be 45,000. 45,150. That's a 5, right? Pretty big number, right? Okay. So again, that's using this formula. However, that wasn't the question, was it? So okay, so this is not the answer. This is the answer to this problem here. Originally, we wanted to start at 5, right? Not at 1. Well, if you think about it, okay, start at 5, right? We want this sum. So that means we have to get rid of these numbers. Well, 1 plus 2 plus 3 plus 4, 3 plus 6, 6 plus 4 is 10, right? So these four numbers, these first four numbers, which were not in the original sum here, add up to 10. So what do we have to do? Well, we have to take this number here, the 45,150, and subtract off the four numbers that weren't here, right? That we're missing. 1 plus 2 plus 3 plus 4 is 10. So just take away 10. And so you're going to get 45,140. Okay. So that's what happens if you don't start at 1. If you don't start at 1, just take away however many numbers you have, right? If you start at 50, you have to, add up from 1 to 49. And in fact, you can use this formula to add up a bunch of numbers, but I figure we're only adding up 4 numbers here, 1 plus 2 plus 3 plus 4. You can do that in your head, right? That's just 10. So that's the number you have to take away from this series because this omits the first 4 numbers. 1 plus 2 plus 3 plus 4 is not in the sum that we wanted originally, the sum up here. Okay, make sense? Yeah. So I just want to get used to this summation notation, so let's look at another example here. Yep, so this will be example 2, I guess. Suppose we want the sum. It doesn't have to be j, right? The book likes to use the letter I. So let's say I goes from 1 to 5 of 1 over I. Okay. So we're not adding the i's, we're adding the reciprocal, right? So let's write out what this means, right? Starting at 1, this is 1 over 1, right? Because I is 1. And then when I is 2, we get 1 over 2. And then when I is 3, we get, 1 over 3. That's 1 over 3. When I is 4, we get 1 over 4. And when I is 5, we get 1 over 5. And that's where we stop, right? We're stopping at the top number here, 5. So we just have to add up these 5 numbers. And yeah, now how do you do that? Well, probably you use a calculator, right? Because you need a common denominator here. And what's the common denominator? Well, I think it's just 2 times 3. I think it's just 5 factorial, which is 120. And so that means you're going to get, let's see, 120 plus 60 plus 40 plus 30 plus it's 120 divided by 520, right? No, 120 divided by 5 is 24? Hang on. Yep, 24. 24. So, all right. 24, right? So that's the numerator. And I almost don't feel like doing this in my head. So 100, 200, 220, 250, 260, 270, 274 over 120. And even that is not in lowest terms. So I must have, yeah, this might not be the best common denominator, the lowest common denominator, but oh well. So 274 divided by 120 is, oh gosh. So if we divide by 2, we get 60, and then 274 divided by 2 is 137. That's got to be it, right? 137 over 60. Oh, God. Sorry. So 137 divided by 60, yep, it's about 2.283, approximately 2.283. And I'm gonna check that again. So hang on. 0.5 plus 0.25 plus 0.2, 2.2833. Yeah, I think that's it. Okay. Right. So yeah, it doesn't have to be i's, right? It could just be you know, the reciprocals of the integer, right? Right. And if that doesn't make sense, let's try another one. Example 3. Right, suppose we're adding up, let's use k now. K goes from 1 to 8 of 2. Okay, so k goes from 1 to 8, and the numbers that we're adding up here are just 2's. So think about what that means here, right? When k is 1, you have 2. When k is 2, you have 2. When k is 3, you have 2. When k is 4, 5, 6, 7, 8. So what are we doing? We're adding up 8 copies of 2. And 2 times 8 is 16. So that's the answer, right? So generally speaking, right, if you're going from, I'll use j again. J goes from 1 to n of some constant c, you're just multiplying n times c. Okay, so remember that. Also remember that when you're going from j equals 1 to n, and you're adding up the integers, you get n times n plus 1 divided by 2. Actually, of course, you don't have to remember that. You don't have to memorize these. If you need them on a test, I'll just give them to you, or you can look them up. But yeah, the point is not necessarily to memorize them. It's to know how to use them, right? And in some cases, we might have to add up not the integers, right, but the squares of the integers. And if you have to do that, you get a formula. It's a little more complicated, right? It's going to be n times n plus 1 times 2n plus 1, all divided by 6. So why is that? Well, take my word for it. It works. Coming up with this is not an easy thing to do. So let's just accept it for its value here and use it later. Oh, so maybe we should write out what this is, right? This is going to be 1 squared plus 2 squared plus 3 squared plus 4 squared, and so on, up until you get to n squared. And if you want to add up the first n squares of the integers, you use this formula here. Okay, and let's do the cubes too. If we do the sum, j going from 1 to n, of j to the power 3, the formula here is going to be n squared times n plus 1 squared divided by 4. Again, where that came from, you know, is anyone's guess. But this is going to be 1 cubed plus 2 cubed plus 3 cubed, and so on, up until you get to n cubed. Okay, so these are handy little formulas that we're going to use over and over again. Again, you don't have to remember them, but you do have to know how to use them. And in fact, let's do one more example. Let's suppose we want the sum. So this, what is this, example 3 or 4? 4, example 4. Suppose we want to, let's say we want I going from, well, yeah, okay. Let's do I going from 1 to 10, but we want to add up, how about 3i squared minus 4i? Okay. So, because you're adding up a bunch of differences here, right? It doesn't matter the order of the differences, right? If that's not clear, write out a few terms and you'll see what I mean, right? This is 3 times 1 squared minus 4 times 1, plus 3 times 2 squared minus 4 times 2, plus 3 times 3 squared, oops, sorry, not 3 cubed, 3 times, well, it is 3 cubed, right? 3 times 3 squared, which is 3 cubed, minus 4 times 3, and so on, right? Up until you get to, sorry, up until you get to 3 times 10 squared minus 4 times 10. Okay? And I'm not writing out the, you know, with I equals 4, 5, 6, 7, 8, 9. Right? They're all in here somewhere, right? So, of course, you can add these numbers first, right? So that's just going to be 3 times 1 squared plus 3 times, 3 times 2 squared plus 3 times 3 squared, up to 3 times 10 squared. And then you can also do, subtract all these numbers, right? So that's going to be minus 4 times 1, minus 4 times 2, minus 4 times 3, minus minus 4 times 10. Right. In other words, I took 3 times the sum, I going from 1 to 10, of I squared, minus 4 times the sum, I going from 1 to 10, of just I. Right. So in other words, yeah, we could split this up as 2 separate series, and then factor out the 3, factor out the 4. Okay? All right. So now what do we do? Well, notice we have a formula for this, and I just erased it. It's way up here somewhere. Yep, it's right here. We're using I instead of J, but don't let that bother you, right? What's the n? What's the top number here? The top number is 10, right? So in our example here, right, n is just 10. So using the formula, right, this is going to be, well, don't forget the 3 on the outside, right? There's going to be a 3 on the outside. And then this sum will be 10, right, times 10 plus 1 is 11, times 2n plus 1. 2 times 10 is 20, and then 20 plus 1 is 21, all divided by 6, right? So that's what you get when you apply this formula up here for the I squareds, or J squareds, right? Right, and then minus 4 times this sum. Now there's no I squared here, it's just I, which is way up here. Okay, it's J here, but you know, J or I doesn't matter. And remember, n is 10, right? So this is going to be, right, 10 times 10 plus 1 divided by 2. So, yep, this is 10 times 10 plus 1 is 11 divided by 2. Right? Okay. So, again, these probably you should just use a calculator, right? So 10 times 11 times 21 is 2310, divide by 6 is 385. So what's in the bracket here is 385. Now, something that you might be worried about here, right? Remember, we're adding up integers. So the answer should not be a non-integer. It should not be a fraction, right? Or a decimal, right? It should be a whole number. But notice that the denominators here, right, are 6. And you might say, well, what if I get an answer of 3,421 divided by 6? Well, that 3,420 should be divisible by 6. In other words, what's in the numerator here will have a factor of 6 that will cancel. And that's what happened here. Okay, so you don't have to worry about that, right? Minus 4 times, so 5 times 11 is 55. In fact, that was the very first example we did, right? Way up here. The first 10 numbers is 55. Right, sorry to make you dizzy, but I just wanted to remind you of that. And that's how we got this very quickly. Okay, so we're still not done. We got to multiply 3 times 385. It's 1155. Oops. 1155. Minus 55 times 4 is 220. So when you take away the 220, you get 935. Oops. Okay. And so that's the answer to this. Right? And so you're just using these formulas up here, right? Okay. So that's summation notation. This is something you have to get used to. If you go on to Calculus 2, you're going to see this a lot. Right? In fact, you're going to see this in a different context, where when you talk about sequences and series, right, you're going to talk about what happens as n gets bigger and bigger, right? And in fact, actually, we're going to do that too a little bit, but so we're not really going to talk about sequences here. But in fact, this is a sequence. It's just a sequence of numbers, right? I just didn't write them all out, but they're all here. Right? So anyways, right? So when you add up a bunch of numbers, of course, you just get another number, right? And this is just the way to express right, the sums of the integers, the squares of the integers, and the cubes of the integers. And if you look hard enough in the book, you can find the sum for j to the 4 and j to the 5, but we're not going to need those. Okay, so this is summation notation, and so now we can talk about area, but you know what? I think I'm going to do that in the next video. So this video is just the summation part, getting used to this symbol. And again, there's a couple of these in the homework where you're just adding up, sometimes a few numbers. Like obviously, is there a formula for this for any n? Probably. I don't know it offhand. But it doesn't matter, right? We're not going to ask you to do this from I equals 1 to 50, right? Because that would take too long. But to do 4 or 5 or 6 of these is not that bad. And even I did it by hand here. You can obviously just plug it in your calculator and get the approximation, or you know how to convert this, right? To get the rational number as expressed as a fraction of integers, right? Anyways, that's all there is to summation notation. And again, if you have questions, just feel free to ask, and I can do more of these if you want.